Okay, we have a couple more different types of indeterminate forms we're going to address in this L'Hopital lesson. So infinity minus infinity is the next one. And the general idea for these subtraction ones I have outlined here. Find the LCD, do the subtraction, and the basic idea is create one fraction. So now maybe you're looking at infinity over infinity or 0 over 0, and you can apply the rule. Okay. So let's take a look at this example. As x goes to 0, 1 over x will go to infinity, and 1 over sine x will as well, because sine of 0 is 0. So here is one of those infinity minus infinity cases. So what I'm going to do is I'm just going to find a common denominator. So I'll multiply the top and bottom of the first one by sine x. And I'll multiply the top and bottom of the second one by x. So that they both have x sine x as their denominator, and then I can actually subtract them. So what happens now? If we plug in 0, I will have sine of 0, 0, minus 0. So this is a 0 on top and 0 on the bottom. So we're going to apply L'Hopital. Take the derivative of the top. I'm going to need a product rule for my derivative of the bottom. And try direct sum again. Okay, so cosine of 0 is 1. 1 minus 1 is 0. X times cosine of x will also give me a 0 since x is approaching 0, and sine x will give me a 0. So I am stuck here at 0 over 0 again. So I'm going to apply L'Hopital's rule again. I need another product rule. So x times negative sine x plus cosine x times 1, and then the derivative of the sine x, which is cosine x. Let's see what happens. So the numerator, everything with the sine x will be a 0, but the cosine x's will give me 1s. So I will end up with 0 over 0 plus 1 plus 1. And so that final result will in fact be 0. We mentioned this before, but just a good thing to add to your notes. Is infinity plus infinity an indeterminate form? And we have said no. And why not? And because adding two large numbers together results in another large number. There's no question there, right? But the question on infinity minus infinity is, what if one of them is really small and one of them is really big? Then they could be approaching infinity, or they could be approaching 0, or maybe they're so close to each other they're approaching a real number. We just don't know. Okay, but adding two things together that are big does not create a conundrum. Okay, and then last but not least, we're going to be dealing with the exponential form. So 0 to the 0, infinity to the 0, and 1 to the infinity. I know that you would think 1 to the infinity would just be 1. But again, if you have a base that's approaching 1 in some way and the exponent is approaching infinity, sometimes it wins out that it actually goes to infinity or it goes to 0. It's hard to say. So here's our process. What we're going to need to do is, if we're taking the limit as x approaches a of f of x to the g of x, so that g of x is the exponent, we need to get the g of x out of the exponent. What technique do you know for getting something out of an exponent? An ln, right? You're going to take an ln and then apply rules of logs. So our first step is going to be to set y equal to this f of x to the g of x that you have. And then you're going to, basically, that's going to lead you to that the natural log of y will be g of x times the natural log of f of x. Right? So that would be just pulling that exponent out front using the log property of logs. Okay. And then you're going to compute the limit as x approaches a of the ln of y. Okay. Of, oops, change my color here, of this thing that you just created, okay, which you will be able to manipulate because basically now you will have it probably in an infinity times zero kind of scenario. So you'll be able to manipulate that to 0 over 0 or infinity over infinity, apply L'Hopital, get your limit. The thing that you have to remember is that what you've just done is calculated the limit of ln y, and you didn't want the limit of ln y, you wanted the limit of y. So how do we undo the ln? We raise it as a power of e, right? So at the very end, you need to raise your answer as a power of e to undo the ln. So, right, if you know that the ln of y approaches L, right, then y is going to approach e to the L because you're basically going to put the e here and the e here, and those will cancel to give you just y. So that's probably the biggest mistake I see on these problems is people get to the end of step 2 and they put a box around it because they're like, oh, I found the limit, which is great, but you got to do that last step. So I got a couple of quick examples here, and let's walk through each one of these. So I have the limit as x approaches 0. If I plug that in, see, if I plug that in here, I'm going to get 1. And if I plug that in here, I'm going to get infinity. So this is 1 to the infinity. So if I set y equal to that thing I'm taking the limit of, then ln of y will be pulling that exponent out front and then the ln of the base. And actually you can kind of already write it in a rational form, numerator and denominator. So now what we're going to do is we're going to try to calculate the limit as x approaches 0 of this ln of the thing we started with. Looks like that gives us 0 over 0. So we apply L'Hopital, which will give us 1. But we're not done because we know that ln of y approaches 1, so y approaches e to the 1. So our final answer is e, or e to the 1. And what lesson was it? There was a lesson where we wrote down that, guess what? E is actually a limit, and it is the limit of this, in fact, this function. So there we just proved it. All right, so go ahead and pause the video, give number 2 a try. Let's take a look. So if I plug in 0, sine of 4 times 0 will be 0, so I have 1, and cotangent of 0 is also 0. That's not right. Cotangent of 0 is not 0. Cotangent of 0 approaches positive infinity. So we have 1 to the infinity. That's what I wrote down. So I'm going to set my y equal to the thing I'm taking the limit of. Take the ln, that will all right, I just noticed a mistake that I made and then I quickly fixed it. So if you notice that everything changed a little bit, that's because it did. So let me go back to where I was. I set my y up right here, and I'm going to take the ln of both sides. So that gives me an ln, which is the part I forgot. The ln of 1 plus 4x, sine of 4x, and then that cotangent comes out front right here, as your property of logs will allow. So then what I'm actually going to do is just move that cotangent down to the denominator, which I could have written it here, I suppose, so that now I have tangent in the denominator because it's the reciprocal of cotangent. That's in that nice rational form, so I'm going to try to plug in 0. Well, ln of 1, which is 0, and tangent of 0, which is 0. I was thinking of that earlier when I said cotangent. So I'm going to L'Hopital. Okay, the derivative of tangent is pretty straightforward. Now, when I do the ln of 1 plus sine of 4x, that will be 1 over 1 plus sine of 4x, so that 1 plus sine of 4x is on the bottom. Then I need to multiply by the derivative of that. I just put it on top for convenience. So that will be cosine of 4x times 4 using the chain rule. So this is 1 over for the ln and then the derivative of the inside on top. If I plug in my 0 again, cosine of 0 is 1, so the top will be 4. Sine of 0 is 0, so that would just be 1. And secant of 0 is 1. So I end up with 4 as my final answer. But it isn't my final answer because I've got to undo the ln through the e process. Now it's my final answer, e to the 4th.